Hi everyone, Part 2, the photoelectric effect. Towards the end of the 19th century, a number of experiments were performed that showed the emission of electrons from a metal surface when it was illuminated with light. This phenomenon was known as the photoelectric effect. It appears that electrons on the metal could gain enough energy from the light striking the metal surface to become totally free of the metal itself. This seems simple enough. Light was believed to be a wave, or believed to be wave-like. Therefore, electrons could be expected to be emitted as soon as they gained enough energy from the light to free themselves. To follow this through, we would expect that the brighter the light, the sooner the electrons would have enough energy to escape. The brighter the light, the greater the energy of the light. This didn't happen. In fact, some very unexpected things happened. Okay, so the unexpected things. When light shines on a metal surface or a photoelectric surface, electrons are emitted and travel across the gap to the anode. Okay, so here's a little picture here. So there's a circuit. Okay, so light shines on this metal surface, this photoelectric metal. Okay, so light shines on that. It kicks off electrons. Electrons then are collected at this little part of the circuit, and they carry on and go around the circuit this way, and you can actually measure a current going on here. Now, just so you're aware, this is the start of solar power. Okay? Solar power, when we get a current from a light source. Okay? Very, very interesting. Now, again, at the time, there was this battle between is light a wave, is light a particle, and the particle people, they were winning up till now. And then this experiment, the photoelectric effect, and the next one, Compton, they kind of showed that, wait a second, light isn't just a wave. It can be thought of as a particle as well, and it's all very crazy. So, anyways, classical physics said that as the wave or more waves hit the electrons get more and more energy, and then when they get enough, they get kicked off. Okay, again, that didn't happen. Okay, so these are the observations from a photoelectric experiment. So electrons are emitted immediately when the light hits the surface. There's no time for the electrons to build up the energy. It happens like bang. So you turn on the light, all of a sudden you get the current. Turn off the light, it stops. Okay, turn on the light and it happens, just bang. Okay, there is a threshold frequency. So if the light shining on the photoelectric surface is below a certain value, okay, no electrons are emitted, no matter how bright the light is. If the frequency of the light is at or above this point, electrons are emitted immediately, even if the low intensity light is used. This certain point is called a threshold frequency. Now, it should be noted that there is also a threshold wavelength, right? Because, of course, we use the formula C equals F lambda. Okay, now C, because it's the speed of light, this is really the universal wave equation, it's usually with a V, but all EMR travels at the speed of light, so C is 3.00 times 10 to the 8th. Okay, so if I have a threshold frequency, and that's denoted by F0, okay, then that also could lead to a threshold wavelength. Okay, so anyways, don't get too caught up in that. But the idea is, if you have a frequency higher than the threshold frequency, electrons are emitted right away. Okay, if you're below the threshold frequency, nothing happens. Wow. Okay, so every metal has its own characteristic threshold frequency. Okay, if the light is at or above the threshold frequency, the energy of the emitted electrons will increase as the frequency of the light is increased. Okay, sure. The more frequency we have, the more energy you have. So if you hit the photoelectric surface with light of higher energy, okay, the electrons just have more energy as they get kicked off. Okay? And then the last one, if the light is at or above the threshold frequency, the intensity or the brightness of the light is increased. Okay, and then the current will also increase. Well, remember, current is simply the number of electrons. Okay, so there's something really weird going on here. Okay, so let's talk about what some of those things are. Okay, these are puzzling and unexpected results. If light was a wave, or if light was wave-like, it would be expected that the intensity or the brightness of the light would determine when the electrons were emitted. It wasn't the intensity that did that, though, it was the frequency. How do we explain threshold frequency? Einstein gave the explanation for the photoelectric effect, for which he received a Nobel Prize in 1921. Okay, it's interesting because everyone remembers Einstein for E equals mc squared. Okay, that's not what he got the Nobel Prize for. His biggest contribution was, or at least the one he's recognized the most for, is the photoelectric effect. It's crazy, because everyone thinks E equals mc squared and relativity and stuff like that, but no, his biggest contribution was the photoelectric effect. Anyways, Einstein explained the photoelectric effect by extending Planck's quantum hypothesis. Einstein said that the light energy was not transferred continuously and evenly as the energy of a wave would be, but it was transferred in bundles. Remember, those bundles are called photons. Okay, he went on to say that the energy of these bundles or photons varied directly with the frequency of light. So remember Planck's quantum hypothesis, E equals hf? Okay, so the energy of the photon is simply E, the frequency of the light is f, okay, and then h, of course, was Planck's constant, 6.63 times 10 to the negative 34, of course, named in honor of Max Planck, who proposed that energy of an atom is not continuous, but occurs in quanta. What Einstein did was to extend this idea of the quanta to include light as well as atoms, okay? So E equals hf, E equals h2 over lambda. We saw those last section. Okay, so these equations allow us to calculate the energy of a photon, okay, given either their wavelength or their frequency. Okay, so we have these little tiny light bundles that have certain energy. Okay, the absorption of a photon by an electron in the metal surface is an all or nothing process. One and only one photon is absorbed by each electron emitted from the metal. This means that the intensity of light, which is the number of photons that hit the electric effect, has nothing to do with whether an electron will be emitted. If the energy of the photon is too low, the electron can't obtain enough energy to escape, so no electrons are emitted. Okay, this explains the threshold frequency. If the photon does not provide this energy, the electron doesn't escape, as electrons require a specific amount of energy to escape. This explains why the electron is emitted without time delay. Okay? It either has enough energy or it doesn't. It also explains why the brightness of light affects the number, or affects the current, or the number of electrons emitted. If we have a really bright light, okay, we perceive a bright light as simply just the number of photons that hit our eyes. Okay, so if all these photons are strong enough to emit electrons, okay, the more electrons can absorb the photons and escape. Okay, we'll get to the summary here in a minute. I want to explain this in slightly easier terms. Okay, so here is a metal, and the electrons sit in the metal, on the metal, whatever, kind of all over. Now, a little photon, I'm going to just draw over the text here, the little photon comes in. Okay, now let's pretend, okay, the metal holds on to the electrons with 10 joules of energy. Let's just pretend. Okay, so if the photon coming in only has 8 joules of energy, okay, the metal's holding on to the electrons with 10 joules. Okay, so this incoming photon doesn't have enough energy to free the electrons. So the photon just goes on its merry way, doesn't do anything. However, if we say that the photon coming in has 18 joules of energy, okay, it only takes 10 to kick off the electron. Okay, so then the photon gets absorbed by the electron. Okay, we have enough to kick it off, so it does get kicked off. Okay, and then it has, so it takes, we started off with 18 joules. It takes 10 to get free, so now the electron gets free of the metal and has 8 joules of energy left over. Okay, that's the idea. That's what's happening. So we have to figure out the energy of the photon, subtract the energy that the metal is holding on with to get the resulting energy of the electron. Okay, we're going to play with that concept in more detail here in a little bit. Okay, so summary. In a photoelectric investigation, the light will always be the manipulated variable. However, there are two ways to vary the light. We can vary it in terms of frequency and intensity. Okay, if the electrons ejected from the photoelectric surface, or the electrons ejected from the photoelectric surface, will always be the responding variable. If the frequency of the light is changed, the energy of the ejected electrons is changed. If the intensity of the light is changed, the number of electrons ejected is changed. Okay, so let's look at this, because we're going to have graphs for this where we have manipulated variables and responding variables. Remember, the manipulated variable is always on the x-axis, and the responding variables are always on the y-axis, or the vertical axis. Okay, so if we manipulate the light, okay, we end up with the electrons. Okay, if we manipulate the frequency, we get energy for the responding. If we manipulate the intensity or the brightness, we have a responding variable of the number of electrons emitted or the current. All right, let's have a look at some of these. Okay, experimental verification of Einstein's explanation of the photoelectric effect was made by Millikan. Now, he is the same guy that found out the charge on the electron. You won't learn that until next unit, but that's okay. So this Millikan guy, he was the one that verified Einstein's explanation. Okay, so let's talk about the math of the photoelectric effect. Okay, so the energy of a photon can be used using either of those formulas. So remember in my little example before? Okay, so that was the 18 coming in. So 18 joules comes in. Okay, hits the photon. If the metal was holding on with 10, then we ejected the electron with 8 joules. Okay, so this energy of the photon, that represents my 18 in my little diagram here. Okay, the energy of the emitted electron can be found using this. So the energy of the electron, okay, so EK max. Okay, so the kinetic energy of this electron is the energy coming in minus the W. Okay, so W, okay, is called the work function. Okay, now that is simply the energy required by the electron to escape from the metal. Now that can be in joules or electron volts. Okay, so this 10 joules in our little example here, that is the work function. The work function is how tightly the metal holds on. Okay, easy enough. So we have the energy of the photon minus the energy that it holds on with, the metal holds on with. Okay, we subtract those, and that is going to be the maximum energy that the electron can have. Okay, now this, of course, this is the version on the formula sheet, can be easily changed. Okay, so remember, HF can be moved to the HC over lambda part. Okay, because that is also the energy of the particle coming in, depending on whether we have frequency or wavelength. Okay, this equation is just saying that the energy of the emitted electron is equal to the energy absorbed from the photon minus the energy it uses to escape. Okay, this equation is basically another example of the law of conservation of energy. Interesting. Okay, energy can't be created or destroyed, so the maximum energy of this electron that gets kicked off is the energy coming in minus the energy it takes to escape. Okay, awesome. So an alternative method to calculate this energy is to use this. EK max equals QE stop. Okay, QE, of course, is the charge on the electron. The EK max is the energy of the emitted electron. Okay, now, V stop, that's an interesting one. In that diagram on the previous page, okay, remember there was this photoelectric cell, and it kind of went around. Okay, it had the ammeter. Okay, and the light waves would come in. Okay, they hit the electrons, and those electrons bounce off. Okay, and you come into this collector and then start going around the circuit. All right, so if I reverse the polarity on this cell and put in a voltage source, like an actual battery here, okay, and I make it so that the electrons go this way. Okay, so basically I take the battery and I switch it around. So now the negative end is this way. So if I do that, what will happen is this end, instead of collecting the electrons, it'll push them away. Okay, so the idea of the stopping voltage is, how big does this voltage have to be to make sure that all these electrons, these emitted electrons, get pushed away from this, the collector. Okay, so that voltage, that energy it takes to stop those electrons. Okay, well, if the electron takes 10 joules of energy to stop, then we know they must have had 10 joules of energy to start with. Okay, it's kind of a backward approach, but it works. Okay, so EK max, of course, is the energy of the emitted electron. QE is the charge on the electron. Well, it's always 1.60, because these are electrons, right? 1.60 times 10 to the negative 19 coulombs. Okay, and then V stop is the voltage required to turn back or stop the electron from reaching the receiver. Okay, that's always going to be measured in volts. Okay, the stopping voltage is measured by reversing the polarity of the photoelectric cell and adjusting the voltage until no electron jumps the gap or reaches the receiver. Wow, clear as mud. Okay, let's keep going. All right, so we got this thing going on here. So, incoming photons. The photons come here, they hit this photoelectric surface. Okay, so when it hits the electrons, if we're above the threshold frequency, electrons will get kicked off. Okay, so the thing is, the electrons will try and go this way across the thing. Okay, now if the voltage is going the wrong direction, okay, what ends up happening is that these electrons get stopped. Okay, so the energy of the electron is found by calculating the energy required to stop the electron. Okay, think of it this way: if the electron requires 5 joules of energy to stop, it must have had 5 joules of kinetic energy to start with. Whew. Okay, one more equation. Okay, work equals HF0. Okay, where W is the work function, so remember that's how tightly the metal holds on. H is Planck's constant, okay, and F0 is the threshold frequency, right? That is the minimum frequency required, or the lowest energy required to kick the electron off. Remember, this formula can also be written in terms of lambda. Okay, so it's Hc over lambda. Now, of course, if this is the threshold frequency, then that is the threshold wavelength. Okay? This really is just a special form of EK max equals HF minus W. Okay? If the energy of the photon is just equal to the work function, okay, the energy required for the electrons to escape, then the energy of the emitted electron is 0. Okay? The electron escapes the metal but doesn't go anywhere, it just kind of hovers there. Okay, in this situation, is at the threshold frequency. We've added just enough energy for the electron to escape, but we haven't given it enough energy to go anywhere. So it just kind of hovers. Okay, notice that when we are talking about the energy of emitted electrons, okay, the term maximum kinetic energy is used, EK max. Okay, because the electron's location in or on the metal, different electrons require slightly different energies to escape, right? So if we have an electron on the surface, it's going to be relatively free to escape. If we have a buried electron, it's going to need a little more energy to escape. So the EK max is just the maximum energy the electron can have. Okay, it could have a little bit less if it requires just a little bit more energy to get off the metal. Okay, so anyway, we always talk about the maximum kinetic energy, so don't worry too much about that. Okay, now the electron on the surface will require less energy to escape than a partially buried or completely buried electron. Electrons with a range of these energies will escape. We only calculate the energy of the most energetic, the maximum energy. Okay, so that's that. Okay, so let's look at some graphs for these things. So if we graph the EK max, so the maximum energy of the electrons, and the frequency of light, okay, we get a graph that looks like this. Okay, nice slope. Okay, as we increase the frequency, the energy of the electrons goes up. Okay, now this point right here, the x-intercept, that is the threshold frequency, the x-intercept. Okay, now if we back this up, okay, this point here, that's the y-intercept. Now, oddly enough, that is the work function. That is how much energy the photon has to give up, okay, in order for the electron to become free. Okay, so that's what happens at the threshold frequency. Okay, and yeah, so the work function will be the y-intercept on these things. And I want to show you something really neat from Math 20, Math 10 even. Okay, so EK max equals HF minus W. Okay, so EK max, I want to show you guys this. Y equals mx plus b. Oh, goodness. Look at that. The y is the EK max. The frequency was the x variable. Okay, the b, remember that was the y-intercept, so that's the w. So what does that mean the slope is? Remember, the slope is rise over run. Okay, so remember, so that's rise over run. Okay, so the slope on these graphs is h. So the slope equals Planck's constant. Okay, now remember, slope is y2 minus y1 over x2 minus x1. Okay, so we might have to use that for some of our assessments later on. Okay, remember you make 2 points so you can find your y2 and your y1 and your x2 and your x1. Okay, remember this will be the point x2, y2, and this will be the point x1, y1. Okay, and we just find the slope. Usually, or in some of the experiments we do, okay, they are, we have to find these points, so or plot them on a graph, and then of course we use a line of best fit, okay, to do that. So when we make our line of best fit, then we pick 2 points off that line. The slope will be Planck's constant. Okay, the x-axis or x-intercept will be the threshold frequency. The y-intercept will be the work function. Okay, and it just works that way. It's really quite brilliant. Okay, this graph is obtained by plotting the maximum kinetic energy of the emitted electrons versus the frequency. Okay, there's a minimum frequency or threshold frequency, and the energy of the electron varies directly with the frequency once the threshold is reached. Remember, that varies directly part, that just means there's a slope, and we just talked about that. The slope is Planck's constant. All right, wow. That was heavy. That's a big section. So anyways, let's do some examples. Hopefully it'll clear some things up for you. Okay, number 1. What is the energy of a photon that has a wavelength of that? Okay, well this is kind of like last unit stuff. So energy of a photon is simply HF or HC over lambda. Now of course we have a wavelength, so we're going to use this one. Okay, so H 6.63 times 10 to the negative 34 joule seconds. Okay, times 3.00 times 10 to the 8th meters per second, all divided by 4 4.60 times 10, what is this? 10 to the 2, and a nanometer is 10 to the negative 9. So remember, these are exponent laws, again, from grade 9, grade 10. Okay, so 10 to the 2 and 10 to the negative 9 makes 10 to the negative 7. Crazy. So 10 to the negative 7 meters. Okay, awesome. So we type that in, 6.63 times 10 to the negative 34 times 3 is 10 to the 8th divided by 4.6 times 10 to the negative 7. Okay, so that energy works out to 3 sig digs, 4.32 times 10 to the negative 19 joules. Okay, so this is, in our little analogy, this is how much energy the photon has coming in. Okay, awesome. All right, so a photoelectric surface has a work function of 2 electron volts. What is the threshold frequency of this surface? So basically, this metal is going to be holding on to those electrons with 2 electron volts. Okay, 2.00. So it's asking how much energy does this photon have to get free, or to kick the electron off. Okay, well, we need 2 electron volts to kick it off. So our E, now we want threshold frequency, so that's E equals HF. And because it's a threshold frequency, we put the little 0 down there. Okay, so I need 2 electron volts. Now remember, the H value is given in both joules and electron volts. So if we have 2 electron volts, we can use the electron volts for H. So that's 4.14 times 10 to the negative 15 electron volt seconds, okay, times F0. Okay, so we just divide and divide. So F0, all right, divide by 4.14. Divide by 4.14. Okay, so 2 divided by 4.14, E negative 15. Okay, so the threshold frequency is 4. Let's see, I got 3 sig digs still, so 4.83 times 10 to the 14th hertz. Okay, so anything higher, so this or higher of a frequency will kick off the electron. If I have a lower frequencies, of course, are lower energies, okay, and if I don't have enough energy, nothing happens. Okay, so this is the minimum frequency I can have to start kicking off electrons. So this or higher will, higher, it's terrible, okay, sorry. I really can spell. This or higher, okay, will cause electrons to be emitted. Okay, emitted. All right, great. All right, number 3. What is the stopping voltage of an electron that has that many joules of kinetic energy? Okay, so once we've done this thing, okay, so we've got this cell, our electrons or our photons have come in, they have kicked off these electrons and they are going towards the collector. Okay, so if this electron has 7.30 times 10 to the 9th joules of energy, how much voltage do I need to apply in reverse to stop that electron? So this is EK max equals QE V stop. So that's how it's written on your formula sheet. So I want the V stop. Okay, so that's going to be EK max divided by the charge on the electron. Okay, so my maximum electric energy, okay, or kinetic energy, sorry, is 7.30 times 10 to the negative 19 joules. And of course, my charge on an electron is 1.60 times 10 to the negative 19 coulombs. Okay, so 7.3 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. Okay, so that is 4 point, okay, I've got 3 sig digs, 4.56 volts. Okay, so I have to supply 4.56 volts to this, okay, to stop those electrons from reaching the collector. Okay, keep going. Number 4. Okay, light with a frequency of 5.00 times 10 to the 14th hertz illuminates a photoelectric surface that has a work function of that. What is the maximum kinetic energy of the ejected electrons? Okay, whoops, sorry guys, there we go. Okay, so we want the maximum kinetic energy, so EK max, that's going to be the energy of the photon coming in, okay, minus the work function. So let's see, we've got maximum kinetic energy, so we've got a work function. Oh, we're using a frequency, so that's going to be the HF minus W. Okay, so this guy is the HF. The W is the energy it takes to kick off. So in that case, the work function is 2.10 times 10 to the negative 19 joules. Okay, so that's the work function, and then the EK max is how much energy the electron has when it gets kicked off. Okay, so HF, so 6.63 times 10 to the negative 34 joule seconds times the frequency, so 5.00 times 10 to the 14th hertz minus W, so 2.10 times 10 to the negative 19 joules. Okay, please notice I used the 6.63 because that's the one that has joules. If the work function had electron volts, I would have used the 4.14 version. Okay, so of course I didn't. Okay, so we've got this going on, so 6.63 times 10 to the negative 34 times 5 times 10 to the 14th. Okay, so this guy, the photon, has 3.32 times 10 to the negative 19 joules of energy. So that's how much energy we have coming in, and it takes 2.1 times 10 to the negative 19 to kick the electron off, so we simply subtract them. Okay, now remember, use all your digits for this because it's 3.315. Okay, times 10 to the negative 19 minus 2.10 times 10 to the negative 19. Okay, and this, again, 3 sig digs, so that works out to 1.22 times 10 to the negative 19 joules. Okay, so that is how much energy the electron has when it gets kicked off. Now, variations of this, I could ask what is the maximum speed of the ejected electrons, in which case this energy is a kinetic energy, so you would just go 1/2 mv squared. Okay, you know the mass of the electron, 9.11 times 10 to the negative 31. It's on your formula sheet. So you could manipulate this and solve for a velocity. So that happens quite often, so don't be surprised when you see that. All right, number 5. Graph the following data on the grid provided. Determine the slope of the line of best fit. What does the slope represent? Okay, so this is, they've given us data for frequency and energy. Remember, frequency is always going to be the manipulated variable, so the x values. Okay, energy is always going to be the responding variable, so those are the y values. So frequency, and again, that's times 10 to the 14th hertz. Okay, good. And then the energy in electron volts. So energy, there we go. Energy, and that's in electron volts. Okay, so let's just have a quick look at what our scale is going to be. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it goes up to 10, just like it says here. Okay, and we only need the frequency to go up to 11.8. Okay, so that's kind of problematic. So cross that off. So we usually want to start at 0, and it's not a huge deal if we don't, but just bear with me. Okay, all right, so let's go up by 2's then. So 2, 4, 6, 8, 10, 12. Okay, so that's kind of as high as we need to go, but let's go one more, 14, just for the fun of it. Okay, and then the energy goes from 0 up to 2. Wow, 2.6, so let's call that 3. So let's see, 0.25, 0.5, 0.75, 1, 1, 2, 3, 2. Oh, so if we do that, we only get up to 2.5. So that's not good enough. So let's go up by 0.5. So this will be 1. 1.5, so this will be 2, 2.5, so this will be 3, 3.5, so that'll be 4. Okay, so when we put numbers like these on the grid, okay, so again, we want to have as close as we can to where the points would be. So let's start at the top here. So our frequency is 11.8. So let's see, 11 is in the middle, so 11.8 is pretty close to 12, so we're kind of along this line here. Okay, so I'm going to erase that. Okay, so we're along that line there, and we're getting up to 2.60. So up here, so 2.5 is that line. So 2.6 would be about there-ish. Okay, so we put the dot on, and then we put a circle around that, kind of to show the error. Okay, so it could be anywhere kind of in that circle. Okay, so then we have 10.6 and 2.11. So 10.6 is kind of along this line. 2.1, so that's 2.5. So 2.1 would be, I don't know, in here somewhere-ish. Okay, circle. Okay, so 9.9 and 1.81. So 9.9 is almost 10. Okay, and 1.5 is there. So 1.8, kind of around there-ish. Okay, 9.1 and 1.47, so 9.1, 1.47, that's just kind of there-ish. Okay, 8.2 and 1.1, so 8.2, 1.1, it's kind of in there. And 6.9, and so that's almost 7, so almost halfway in there, and 0.57, so that's 0.5. 0.57, so kind of in there-ish. Okay. Now, you, of course, would use a ruler for this. I'm going to try and use a straight edge, but I think it's going to... it might not. Okay, I'm going to use a straight edge. Okay, you, of course, use a ruler. Now, you want the line of best fit. So we're going to make this, so kind of your best line you can. Some over, some under. Okay. So that's pretty close. We've got kind of 1, 2 kind of under, 2 over, and 2 kind of right on. Okay, so that's the idea for your line of best fit. Okay, so we determine the slope. Remember, when you want slope, you can't use the points from that you plotted. You have to use points on your line of best fit. So you know what? I'm going to write in red now so you can see it better. Okay, so look, we want perfect-ish points. So that's a perfect point. So let's see, that's going to be 16, and oh look, that's 4.5. Okay, so just write it down, 16 and 4.5. I guess technically 16.0, because we can kind of read these graphs to the nearest tenth, like that's pretty accurate there. Okay, now the other one, so you look down the graph, usually you can find a couple of perfect points, and that one right there, that's pretty perfect. Okay, so let's see, that's going to be 8.0 and 1.0. Okay, so actually write the coordinates. Awesome. Now, of course, slope is rise over run. which is y2 minus y1 over x2 minus x1. So I'm going to make this one y, or x2 and y2. This one will be x1, y1. Okay, so y2, so 4.5. Okay, and now remember, these are electron volts, so 4.5 electron volts minus y1 is 1.0 electron volts divided by, now x2 is 16.0, but remember that's times 10 to the 14, so 16.0 times 10 to the 14th hertz minus x1 was 8.0. 0.0 times 10 to the 14th hertz. Awesome. Okay, so when we multiply that or figure that out, okay, using brackets, so 4.5 electron volts minus 1 divided by 16.0 times 10 to the 14th minus 8 times 10 to the 14th. Okay, so when we type that in, we get 2 sig digs is all we get, so 4.4 times 10 to the negative 15. Okay, and remember this is going to be EV. Now, technically it's electron volts per hertz. Electron volts divided by hertz. However, remember our hertz is a 1 over second, so I go right over here. Okay, divided by 1 over seconds. Now remember, we can't have fractions inside fractions. So how do we divide fractions? Remember, we flip and multiply. Oh, so that S just comes up. So it's EV times S divided by 1, which is just EV times S. Hey, look at that. 4.4 times 10 to the negative 15. Remember what we talked about earlier. The slope of this is always Planck's constant. And if you look, Planck's constant is really 4.14 times 10 to the negative 15. So we got awfully close with our pretty sketchy data. Okay, so that is Planck's constant. Okay, so there's the slope, and of course it represents Planck's constant. Ta-da! Awesome. Okay, and then one more for this. Okay, so given the following data, graph the data on the grid provided, determine the slope of the line of best fit. What does it represent this time? Okay, so same sort of deal. Frequency is the x's, stopping voltage is the y's. Okay, so this time we're going from 5 to 8 for frequency. So if we start at 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's enough. So we can go up by 1s. 9, 10. So this is going to be frequency again times 10 to the 14th hertz. Okay, and then of course we have stopping voltage. Okay, so stopping voltage goes from 1 up to not even 2. So look, this time we can go. So 0.25, 0.5, 1.75, then 1 would be there. 1.25, 0.5, 0.75, so 2 would be there. So we can go up by 0.25s. Okay, so stopping voltage is in V, volts. Okay, and the point here, remember, we want to use as much of the graph as we can. Okay, so that's the idea there. So now we plot our points. So 8.214, okay, for frequency, and then a voltage of 1.835. Remember, we can't get that accurate on our graph, so that's why that we put the circle around the points to represent kind of the error. So 8.2 is kind of along this line. Okay, 8.2 and 1.8. So look, that's 1.0, 1.25, 1.5, 1.75. So 8.3 would be around here-ish somewhere. Okay, and circle. Okay, that's a pretty big circle. All right, good enough. All right, so 7.4 and 1.4. So 7.5 is halfway, so 7.4 is slightly less than half. Okay, and then this is 1.428. So 1.5 is here, so 1.42 kind of down in around here somewhere-ish. Okay, awesome. All right, 6.879, so that's almost 6.9, so that's pretty close to 7. Okay, and 1.24. Hey, that's awfully close to 1.25, so it's not on that line, but just below that line. Okay, pretty close. Okay, 5.49, so like 5.5, and 0.67, so 5.5 is kind of right in the middle-ish. Okay, and 0.67, so that's 0.5 there, so 0.6, almost 0.7, so probably a little higher than that, sorry. So probably about right there-ish. Okay, again, we want to be as close as we can. Okay, and then 5.2-ish, 5.2 and 0.551, so it's kind of like in there. 5.2, 0.55, so kind of there. All right, so there's our points. So let's make our line of best fit here. So kind of around there somewhere. Okay, awesome. Okay, so again, use a ruler when you make a line of best fit. Like that's kind of a big deal. Okay, now perfect points. Here, I'll draw in blue again so we can distinguish. Okay, so perfect points. Let's see, this one is pretty close, as is this one. Okay, so that point, so X is 7.0, and then Y is 1.25. Okay, and then this guy, of course, is at 4 and 0. All right, we'll interpret that in a minute. So it said graph the data, determine the slope. Okay, so slope is simply y2 minus y1 over x2 minus x1. All right, so the slope, so y2, 1.25. Now remember, this is voltage, 1.25 volts. Now look, the only reason I can go to 1.25 is because it's right on the crosshairs there, so we can get down to that nearest hundredth. If you were forced to use, say, this point, so you look up here, guys. If you were forced to use that point, you'd probably be accurate to say, okay, so that's 1.75. All right, so that's maybe like 1.5, 1.75, so maybe 1.7. Okay, yeah, so you can guesstimate nearest tenth. The only reason I was able to go to the nearest hundredth because this line is 1.25. 1.5, 1.75. Okay, so anyway, sig digs on graphs are sticky. Okay, anyway, so 1.25 minus, okay, so then the y coordinate over, oh, look, that's 0. Well, that's cool. Okay, and then the x's are 7.0. Now, remember, these ones are 10 to the 14th hertz minus 4.00 times 10 to the 14 hertz. Okay, so 1.25 minus 0 is simply 1.25. 5 volts divided by 7 times 10 to the 14th. Whoop, type that in wrong. 7 times 10 to the 14th minus 4 times 10 to the 14th. Okay, so our slope here is 4. Really, we've only got the 2 sig digs here. So 4.2 times 10 to the negative 15th. Okay, now we have a volts per hertz. Now that's going to be the same kind of thing. So volts divided by hertz is volts divided by 1 over seconds. So that is a volt second. Okay, so that's that guy. So that is our slope. Now, as far as the second part goes, what does the slope represent? That's a little trickier because the units for this are volts times seconds. Now, remember, volts and electron volts are very different things. Voltage is electric potential energy, whereas electron volts are just energy. Okay, so very, very different things. So let's erase this and give myself some space. Okay, so the slope as it's written doesn't really represent much at all. Okay, however, so the slope represents volt seconds. So again, not particularly helpful. However, I want to show you how we can use this slope to figure out Planck's constant, because that's where questions on your summative assessments and your diploma exam are going to force you to go with stuff like this. Okay, so it's going to be a little bit of algebra, so just a warning and a heads up. Okay, so just walk with me, go step by step, and then you can come back to this as you have questions that deal with this kind of stuff. All right, so we know the formula for this. So if we look stopping voltage and frequency, okay, we want to try and find some formulas that have these things. So on our formula sheet, we have EK max equals QE V stop. Okay, so that's kind of where we go first. Okay, because this has the stopping voltage. All right. Now, frequency and stopping voltage really don't go together, but frequency does figure into the EK max formulas. So EK max, remember, that was HF minus W. Well, there's another little formula on your formula sheet for W. W equals HF0, right? Now, remember, the threshold frequency is the x-intercept, so that's that point right there, the 4.0 times 10 to the 14th hertz. Anyways, that's neither here nor there. But anyways, so we can rewrite this as EK max equals HF minus HF0. Okay, now see how both terms have an H in it? So we can factor that H out. Oh, you thought you were done with factoring, didn't you? Okay, so F minus F0. Now remember, the frequency minus the threshold frequency, guys, that is simply a delta F, okay, or a change in frequency. Well, funny how on a graph from this point up to that point, that is your delta F. So that is simply your x coordinates. Okay, so tell you what, this is the EK max, so let's substitute that over here. H times delta F equals QE. Now look, our V stop, okay, our frequency is our X, our V stop is our Y. Now remember, slope equals the change in Y, the rise, over the change in X. Oh, isn't that interesting? So it's our y's divided by our x's. So if I take this, and I know this is heady, so just bear with me. Okay, if I divide my frequency down there, okay, I'm going to get y divided by x. So now, of course, we have to take that QE and divide over here. Okay, so watch what happens when I do that. I get my H divided by my QE, which is the charge on the electron, is equal to my y over my x. Okay, now really, guys, this y over x, that's just our slope. Oh, okay. Well, so follow through with me one more time. So h divided by QE is equal to, on my line of best fit, now hopefully yours is close, like we might have slightly different answers because our lines of best fit are going to be different. Okay, this is how I know that you can't cheat off your friends, because you're all going to have different lines of best fit. Okay, so there's how we apply our slope. So our slope represents Planck's constant divided by the charge. Okay, now in order to find Planck's constant, because usually questions that are really crazy hard say use the data to find Planck's constant. Now, on that last question, Planck's constant was simply the slope. Okay, and that made sense because we had the energy and the frequency. However, this time we have energy and stopping voltage. They don't play together quite as nicely. However, if we multiply the QE up, because QE, of course, is an electron, so 1.60 times 10 to the negative 19 coulombs, watch this. So when we multiply those two things together, 4.2 times 10 to the negative 15 times 1.60 times 10 to the negative 19 coulombs. Okay, now remember, a volt times a coulomb is an energy. That's joules. Oh, so this works out to 4.2 times 10 to the 15 times 1.6. So 6.7 times 10 to the negative 34 joule seconds. Now compare that to the original, or the accepted value of 6.34 times 10 to the negative 34 joule seconds. See, that's awfully close to Planck's constant. Okay, so that's kind of where we go from there. It's a little on the crazy side. Pardon me, 6.34. Haha, funny. 6.63. That's a lot closer, isn't it? 6.63 times 10 to the negative 34. So this is very, very close using our data. So on graphs like this, and you will have them in the assessments, okay, you have to do a little bit of algebra to figure out what that slope represents. You always relate it back to questions that you have, okay, and then you can figure out Planck's constant from that. Wow, that was a lot, but believe me, you're more than capable of doing this. This will be great. Okay, so I want you to practice this stuff. Page 720, I want you guys to do 1 through 10. Do them all. It's good practice. Okay, again, you can use your textbook or print that page out in the workspace card. Just then you can write all over it. You might want to use a loose leaf anyway, so totally up to you. See you guys next section. Thanks.